Hey everyone, this is Team 15, and we are proud to present Opus, a new take on music education. Learning music is a luxury that is expensive, and even when it is affordable, lesson infrequency impedes progress. The value of a music education is well documented, including forming special regions on the surface of the brain, better SAT scores, and better appreciation for music later in life. The biggest reason people quit is because they get bored and don't practice. One way people overcome this is through music education games. Examples being Simply Piano and Guitar Hero. While these games have had varied success, we seek to overcome their weaknesses while adding our own creative touch to make a unique and worthwhile education tool. In rhythm games, like Guitar Hero, the player is captivated but does not learn much because they are on fake instruments. In music education games, like Simply Piano, the joy of gaming is lost because the user reads straight off of sheet music. Opus aims to cover all these weaknesses while truly maintaining the essence of a game, where fun comes first.
In order to make an exciting game while also having performant audio processing capabilities, our team decided on using Unity to develop the game and Apple's Accelerate and Foundation frameworks for digital signals processing. Unity provides flexibility in development and a large community for support. Accelerate and Foundation are iOS native frameworks that provide us with access to raw audio data with minimal latency, as well as access to low-level DSP functions to use when implementing our node detection algorithm.
For our minimum viable products, we detected notes on a piano from C7 to C8, created the first world of the game which taught the user how to play scales, achieved a maximum latency of 1 second, and ran the pitch detection and the Unity game independently on a Mac.
All of the nice-to-haves have been met. We can detect the 32 white keys on a grand piano, and we have created all 5 game worlds, each demonstrating a different skill or audio quality that we can measure. The game runs on iOS only, and our latency is well within the 0.1 second window. If we have more time, we will tackle some of our moonshot goals, but they require more technical work, such as deep learning models and MIDI transformations that will be touched upon later.
For this project, we split into 3 teams. First, we will take a look at the game built from scratch in Unity. Then, we will analyze the digital signal processing techniques that let the app analyze notes. And finally, we will take a look at the integration that brings it all together.
To begin, we will first discuss the game itself. Here's a short trailer of the different game worlds. Each world covers a different music concept that we have gamified into discrete skills. World 1 covers majors, World 2 covers timings, World 3 covers minor scales, World 4 covers chords, and World 5 covers tempo.
Before we demoed the game at the end, we wanted to talk about our building process. As time went on, our affinity with Unity grew as we learned how to master Unity and C#. We began by using drag and drop elements to create World 1 and transitioned to programmatically spawn recurring assets in later worlds. The game progressed from a single update thread to a multi-threaded approach to speed up the game. We made small optimizations to be able to capture frame-perfect data, including syncing frame-perfect animation data with pitch detection data.
We were inspired by old 2D platformers like Super Mario World and wanted to bring back the 3D effects like parallax, an early technique whereby the backgrounds move at variable speeds relative to the world speed. To achieve the parallax effect, we employed some code to move the background pieces every frame to achieve a ratio of the set world speed. Some worlds had as many as 20 plus parallax objects moving at various speeds.
One principle that old 2D platformers had to be wary of is resource management, and because the audio processing takes up a large amount of the phone's resources, we faced similar issues. Game levels can easily reach hundreds of assets that need to be on the screen at the same time, each with their own behavior. Spawning all the enemies at once, even those off-screen, would have been a big burden to our processing power and would have affected the speed and quality of our gameplay. So we implemented programmatically spawning our enemies so that only one enemy needs to be accounted for at any given time, reducing the workload of our processing. Once again, taking inspiration from older games, we decided to stick to 16-bit graphics, where each character sprite would be no more bigger than 100 by 100 pixels. While each sprite seems like it wouldn't need too much work due to their low pixel count, creating multiple sprite sheets where each character can be animated as fast as 16 frames per second requires numerous cells that need to be handcrafted each. The limited number of pixels per frame also brings about the issue of not being able to be as complex as a real image, and therefore required us to think about how we could bring forth the identity of the sprite in a limited format.
Shown here is the average schema for any given world. Each world is connected to the main screen by transitioning to different scenes. Each world references the same static classes to keep configurations across worlds consistent. Each world has a level controller that the iOS integration references to pass pitch detection data. Depending on the level, there may be one or more classes not showing up in the schema, including animation controller classes and collision detection.
Before we attempt pitch detection, we need to understand what a piano note looks like in the frequency domain. A piano note, for example middle C, consists of the fundamental frequency and its harmonics. The fundamental frequency is what you hear, or the frequency that is uniquely associated with the note, like middle C. The harmonics are multiples of middle C that are unique to each instrument and make up the timbre of that instrument. The challenge is to identify the fundamental frequency out of all of a note's frequency components so we can accurately detect the note being played. Performing an FFT, or fast Fourier transform, on the signal is not enough because of the complications introduced by timbre. Other algorithms that we tried would inaccurately detect a harmonic instead of the fundamental. We found that the HPS, or harmonic product spectrum, to be the best algorithm for us because it is accurate and operates in real time, which matches the latency requirements of our game. However, HPS alone is only good for detecting one note at a time. Multi-pitch detection is still an open research problem and it is hard to do a completely accurate analysis, especially in real time. With single pitch detection, we had prior knowledge of how many notes we were searching for, but with multi-pitch detection, we lose that prior knowledge and the pitch identification process becomes much more complicated. We found that it is difficult to approach multi-pitch detection in the time domain, so our solution we found is a modified version of the HPS which uses an FFT in the algorithm. This algorithm utilizes thresholds relative to the maximum pitch to classify other pitches into real pitches and uncertain pitches. The real pitches are pitches that we are confident enough that are being played because they are prominent enough to be above the threshold. The energy of the uncertain pitches and their harmonics are then further analyzed to see if they could be real pitches too.
In order to detect notes, we needed a way to reliably fetch a stream of raw audio signals from the iPhone microphone. After extensive testing, we landed on using Apple's native audio interface implementation in order to meet our performance requirements. Using their API, we were able to set a sampling rate of 48 kHz from which we fed samples every third of a second to get a buffer size of 16,000 samples. This, according to the Nyquist-Shannon theorem, is the minimum set of samples we need to reliably detect all frequencies on a 108-key piano. Once we had a consistent stream of audio samples, we ran into an issue where our algorithm detected what seemed to be random frequencies stemming from background noise. We solved this problem by identifying the power of the background noise signal. Then we analyzed our sample stream only if its power level is greater than the background noise threshold. This simple fix helped to double our precision in detecting piano notes. At this stage, we found that while our audio processing was good, it wasn't perfect. Our audio processing rate was less than a third of the game's processing speed, and this presented a discernible lag for the user. We solved this problem by creating a sliding window for our audio samples. By creating a dynamic buffer of 16,000 samples, we're able to collect smaller chunks of audio samples at a more frequent rate without sacrificing our sample size requirement for detecting the entire range of frequencies. This solution creates a continuous flow of audio data and results in a much more responsive feel in the game for the user as it increases our note detection speed by over 250%.
Eventually, it came time to put it all together. We solved problems such as ensuring iOS sees Unity as an external library, having bridge code that could handle Swift in particular, and even circumvented bugs that were inherent to certain versions of iOS. Above all, we had to ensure that we weren't introducing extra latency with our two-layered solution. In testing, we found that on average, it took 17 milliseconds to send data from iOS to Unity, which is much faster than the rate at which the game updates. This speed is consistent across multiple different types of iPhones and is more than fast enough for our requirement. If we look at a competing app such as Simply Piano, we find it can consistently detect multiple simultaneous notes in real time. While our polyphonic note detection algorithm is a good start for our use case, there are many things that we can learn in the future from an app like Simply Piano. We explore how a deep learning approach may be a solution to this problem in our paper if you are interested.
Okay, second rotation.
While the goal of this project is primarily education, we knew we wanted to take a different approach from simply having sheet music scroll across the screen. We wanted to incorporate all the joy, wonder, and sense of accomplishment that comes from playing video games. In striving for this experience, we used the unique capabilities of our phones to make a product that is not only accessible and practical, but also rewarding to play. As engineers, we face numerous technical challenges to create this integrated product. On the Unity side, we made the game efficient and scalable through strong software engineering fundamentals. Furthermore, we made it thematically unique and fun to play by creating original artwork. On the iOS side, we can identify musical notes from sound in the environment through various algorithmic techniques that we researched from scratch. Lastly, we integrated these two layers, allowing anyone with an iPhone and an instrument to start learning musical fundamentals such as scales, tempos, triads, and more.
We are happy of what we achieved this semester, and we hope that you found it interesting. We would like to thank our advisor, Professor Wahid Bajwa, for his guidance this semester. Thank you for watching our presentation.